Welcome back. This is module 2 of chromatography. So you'll recall chromatography involves the separation of compounds based on their different affinity for two phases, a mobile phase and a stationary phase. So in module 1, we looked at how silica gel as a stationary phase and the various organic solvents used could affect the way the molecules partition. In module 2, we're going to take a look at an extension of these principles to another technique known as column chromatography. Whereas TLC is kind of used as what we call an analytical technique. I look, I see how many spots I have, I see which one is more polar, or maybe which one matches a given material reference. Column chromatography is what we call preparative, meaning that it allows us to actually separate the components of a mixture and isolate them and obtain the compounds at the end. Okay, so it's a larger scale version. A lot of the principles are exactly the same. So we're going to take a look at how it's similar and how it's different. At the end of the module, we're also going to run through the workflow for our column chromatography experiment that we'll carry out in lab during week 1. The goals of this experiment are first to use TLC, the analytical technique, to identify the best mobile phase for our column chromatography separation, and then to actually carry out a separation of the active ingredients of an analgesic commercially available tablet from one another. Shown here on the right is a column chromatography setup. So you can see that it's larger in size than a TLC plate. And in this case, the molecules are nicely colored so you can visualize their separation along the stationary phase. Okay, so when we consider a column chromatography setup, it's a little different than the beaker-based developing chamber we used for TLC. So I want to start by taking a look at the bones and all of the components here that we need to make a column chromatography apparatus. So instead of using a plate, for column chromatography, we're going to use a glass column. And that glass column is going to have a plug at the bottom and some version of a tube that can be opened and closed to allow the flow of mobile phase through. In our case, we're going to place a cotton and sand plug down here at the bottom. So this is going to prevent the packing of the solid phase from leaking. Okay, so we're going to have a sand and cotton plug, and then we're going to have a tube with a release valve to control the flow of solvent. So within this glass container, okay, within this glass column, we are going to have our components of chromatography. We're going to have our stationary phase, which will still be silica gel. Instead of having a thin coating of this powder though, now we will have a few grams of the gel packed into the column. Okay. And the gel will be wet with an organic solvent that will act as our mobile phase. Okay. So what is different about the chromatography setup within the column as compared to the plate? As you can tell, it's obviously a larger scale. The other thing that's different is in a TLC plate, we watched solvent travel up the plate and it brought the molecules with it. In the column, we're going to be adding solvent through the top, and the solvent mobile phase will travel through this silica gel column via gravity or with the help of a little forced air. moving the molecules downward. Okay, so this is the big difference between a TLC plate and a packed column. So how can we think about this and use the principles that we discussed in Module 1 to predict the order that compounds will elute from our column? The easiest way that I could think about this is that you can parallel this column and think of it as a upside down TLC plate. Okay, so let's start with a plate because we've become familiar with those. If I look at the plate shown here on the bottom, I have some mixture of compounds represented by yellow and blue. Okay, what we know from our previous discussion is that the blue compound has a lower or smaller RF value, meaning it sticks more tightly to the silica gel stationary phase. Thus, we know that that molecule must be more polar. Okay. Our yellow molecule, shown here, travels farther up the plate, meaning it does not absorb onto the polar silica gel as tightly, and thus it has a higher RF. Or we said in the last module, we could think about this, that this travels faster through the stationary phase. Okay. So this molecule sends more of its time traveling away with the solvent. Okay. So if we think about a column chromatography scenario, like the one you're going to carry out in lab, you're going to take your mixture isolated from the analgesic tablet, and you're going to load it onto the top of the column. Okay. So by contrast, in TLC, we loaded it onto the bottom or the baseline of the plate. Once the molecules have absorbed onto the silica gel, we're going to pass the mobile phase through the column. As we've seen, the molecules will begin to partition themselves by desorbing from the silica gel and traveling to some degree with the mobile phase, and then reabsorbing onto that stationary phase. Well, as our TLC plate predicts, the yellow molecule is going to spend less time on the solid stationary phase, and it's going to spend a greater portion of time traveling with the solvent. So by column chromatography, we would expect the yellow molecule will travel down faster. Okay, so the less polar moves out of the column faster. And in this nice pictorial representation, which you could see as the molecules start to separate, and then the yellow keeps on moving and completely exits the column before the more polar blue compound. The blue compound that's interacting more strongly with the silica gel will take more time or might even require a different mobile phase to pull it off of the column. Okay. So this is how you can predict what we call order of elution or exiting of the column based on TLC data. So this will be important because as part of today's experiment, you're going to be obtaining TLC data on the components of the analgesic pill you're interested in first. And you're going to use that data to inform you as to say which one will come off of your column first and what solvent to use as the mobile phase for your column to give this nice separation. Okay, so when we come into lab, you're going to grab your personal tote, suit up with your PPE, and then we're going to get to work. The lab assistants and I will assign you a mobile phase to try, okay? And what you're going to be given is a standard solution of acetaminophen and a standard solution of caffeine. You'll either be given a mixture of the two, Or you can get a feel for how they separate from each other when together by creating a mixture, by mixing a little bit of them together. Okay. So what you're going to do is you're going to first prepare your developing chamber. So you'll recall that you're going to have your beaker, and you're going to place into the beaker your assigned mobile phase, recalling not to fill that beaker too high, okay? Then you're going to be given a TLC plate, and with clean hands, you're going to spot a small portion using a capillary tube of each solution onto your TLC plate's baseline. Okay. Recall that you're going to mark this with a pencil. Let's say you've been assigned 100% ethyl acetate as your solvent. You will place that in the beaker and you will develop the plate. When you remove the plate from the beaker, it's important to think about how you would decide if that solvent would make a good separation solvent. So, in a mobile phase for chromatography, we want to see distinct separation between the two compounds we're looking at. The components of the mixture. Okay, so we want to see that distinct separation. Other things to consider is sort of what's an ideal RF, okay? We don't want the RF to be 1, meaning we don't want to find our compounds all the way at the top of the plate. If they're traveling that high up, it can be very difficult to distinguish them from one another. We also don't want an RF close to 0. Okay. Then they'll be all the way at the bottom and they might not truly separate. So what we're looking for is we're looking for an RF of maybe, about 0.3 to 0.6. We're looking to find our compounds here in the middle of the plate with nice separation. So each assigned student will share a picture of their data with the group, and we will come to consensus. And for this experiment, we're going to choose one mobile phase that we all agree should give us an effective separation of the molecules. Okay, so once we have chosen that mobile phase, we have to isolate these active ingredients that we're interested in from the analgesic pill itself. Okay. So in your hood, you'll find a mortar and pestle, and you'll have been given 1 tablet. You want to grind that up to access all of the good stuff that's inside the tablet. And you're going to dissolve it up in a little bit of ethyl acetate. Okay, your procedure has the specific volumes. We're going to gently heat this. You will notice that some of the components within the pill are not soluble in this organic solvent. Think about what those might be and why, for a pill that you're ingesting into your body, it might be advantageous to have those be water soluble. Once we have isolated these organic soluble components, we'll have some solids, so the insoluble solids left over. We don't care about those. That's not where we're going to find the acetaminophen and the caffeine that we're looking to separate by chromatography. The way we're going to remove those is by something known as gravity filtration. In the gravity filtration, you'll have a filter funnel. So you'll have a glass funnel here. And inside of that glass funnel, you will place a fluted filter paper. You can pre-wet the paper with a little bit of ethyl acetate to help it stick to the glass funnel and not leave you gaps. You're simply going to pour your warm solution through that funnel into a clean glass beaker. Okay. Once you have that solution, you now have, hopefully, a solubilized, clear solution of acetaminophen and caffeine that doesn't contain any of this insoluble junk we don't care about. You're going to be given a plastic pipette that has a 1 ml marcation at the top, and you're carefully going to take a ml of that solution and add it onto your column. Okay. So as you're thinking about the way your workflow is going to go for the day, this is what your hood setup is going to look like. You're going to have your mortar and pestle, okay? And you're going to have your beaker so that you can dissolve in ethyl acetate, along with a hot plate. So you will find all of this in your hood when you come in. Additionally, you'll find your TLC chamber, okay? And you'll have a variety of the solvents you need. Ethyl acetate and ethanol will be most of the solvents that we're studying by TLC. And some mixture of the two will likely be chosen for the column chromatography mobile phase. So you'll have your solvents over to the right of the hood, okay? Once you have your 1 ml solution, your dissolved solution, your gravity filter will be set up on a ring stand so that you can not have to juggle too many things in your 2 hands. And your clean beaker will be adjacent to it. Okay. You can go ahead and carry out the gravity filtration, and then you're ready to add that 1 ml solution onto your column. In column chromatography, it's really important that before you adsorb your material on, the column has been pre-wet with the mobile phase. We have to make sure that there's no air holes and cracks in this column, because as your molecules are traveling, that will disrupt their movement and thus their separation from each other. To facilitate this and make this lab doable in the time allotted, your column will be pre-wet with an appropriate mobile phase, okay? So you can go ahead and add your 1 ml directly on and let it adsorb onto the silica gel. You will need to make some of the mobile phase we have selected as a group, and there will be a large beaker and some graduated cylinders in your hood so that you can do that. Here's a close-up of what the column will look like. So as we mentioned in the beginning of this module, here's your glass. It has been pre-packed with a silica gel and pre-wet with a mobile phase. Here's your cotton and sand plug and your tip with a removable clamp so that you can control the flow of solvent in and out of the column. Okay. So once your column has been loaded and your 1 ml solution has been added, you're ready to begin collecting what we call fractions. So you'll have a bunch of small beakers, and you could label the first one as 1, and you could begin to allow the solvent to exit the column. As that solvent comes out, you will continue to add additional mobile phase, and you will collect beakers 2, 3, 4, etc. No more than about 20 mils per beaker. We don't want to collect everything in one beaker because then we won't obtain separation as our molecules elute at different times. Okay. So that is what we call running a column. The way that you're going to look at your fractions is you're going to obtain a new TLC plate, and you're going to spot a little bit of solution, 1, 2, 3, etc., into each lane of a TLC plate and develop it. Once both of your molecules have been observed on the TLC plate, you know that you have eluted them from the column, and you can assess how well you achieved the separation of them based on how many spots are observed in each individual fraction. So that's going to be today's experiment. Column chromatography has wide use, especially in industrial pharmaceutical labs where scientists are striving to make really clean active ingredients that can go into formulation for instance, a drug you might be taking. Of course, as you get into these larger scale labs, we get a little help, and there are automated systems available. And after running a column, you'll have an appreciation for the fact that these automated systems pump the mobile phase through your column and collect it into individual fractions. So while you're at lunch or checking your Instagram, this column can be running for you. But for this week, we're going to do it old school and simple, and you're going to run for yourself. So I will see you for the first week of lab. Please reach out with any questions, and have a great week.